Good afternoon, guys. I hope you hear me well. We are going to start the session, exceptional session, to continue our Cisco lessons covering today Module 8 and Module 9. Just to remind, before we were talking about Layer 2 from the OSI model, which is a link, data link layer. And there we are working with the MAC addresses. Today we're going to discuss the third layer in the OSI model, the network layer. Plus, additionally, we're going to discuss some IP addressing of the protocols IP version 4 and IP version 6. Before this, but I just want to tell you that the packet tracer assignment that I have asked before to make and to cover in for certain time, only few students were doing on time, so only these students were taking grades. The other students that submitted after the date, the due date, couldn't be graded. That's why automatically on the system comes 0. So next time, please be aware of this. When we have a packet tracer, probably in January, I'm going to give. Today, just we have to discuss these two modules and nothing to work in the academy. We're going to talk about this again, but anyway, I explained the situation if you have seen your grades in the Cisco Academy. So let's start. We're going to discuss, as I said, in Module 8, the IP version 4 and IP version 6 addressing, also the packets and the structure of the packets in these protocols. We're going to discuss also some additional material about how the routers will work executing the information that is provided by the IP headers, and some introduction about the routing table. What are the network layer characteristics? As you see here in the OSI model, the 7-layer OSI model, this is the third layer, which if we have to follow these layers from the application, the highest 7 layer, and going downward to reach the physical layer, we have to say that this third layer provides also some encapsulation according to the protocols that we have here. Actually, if you have two end devices, like what is on the picture, these end devices are given IP addresses. Yeah. So these IP addresses are provided statically or manually by the administrator or by the user. Or if you are in a network, which is, let's say you have a wired network, probably you use DHCP server, where automatically you receive your IP addresses from the IP pool provided by the server. Now, what we can see in the network layer, mainly here we work with two protocols, IP protocol, Internet Protocol version 4 and IP protocol version 6. Here also we have to discuss the 4 basic operations that are provided. First of all, we have to previously to provide the addressing of the end devices, as I said. When these devices start to send their packets to the intermediary devices, like switches and routers, we have to say that there must be some process of encapsulation, where the routers will de-encapsulate the frames coming from layer 2. Okay, if you remember this, they encapsulate the MAC header that is at the beginning, and after they read the IP addresses for the source and destination in this packet. So after reading the destination IP address, the router must provide some process of routing, looking up in its routing table, where it must find a matching entry where this packet is going to be forwarded in order to reach the destination. Before forwarding the packet, the router must encapsulate again the layer 2 data, which is forwarding the layer 3 data, and after the router is going to forward the packet through one of the interfaces of its own. So these are the 4 basic operations: addressing end devices, encapsulation, which means we add some information about the IP addresses of the source and destination in a header of the packet. After, we have a routing, which is the process in the routers that decides where to forward the packet from. And the encapsulation, this is command, another characteristic that concerns how the router will discover the IP addressing inside the packet. And here we're going to discuss this more. Now, let's say we are in the layer 4, which is the transport layer, and the data that is encapsulated here is data that comes from some application. So this is what we call it data payload. From its side, the layer 4 transport layer provides its own segment header. We're going to study this in the next module next time. And after providing this segment header, the transport layer moves this bunch of data into the layer 3, the network layer. So from the side of the network layer, the whole data, the payload plus the segment header of the transport layer, we consider as a data payload, and we add the IP header for this data payload. As I said, here in the IP header, we have the source and destination IP addresses. So as you see here, we have the network layer. Downward, we have what? Data link layer that from its side is going to map, additionally to this IP header, will be mapped the MAC addresses of the source and destination. This is what we call it layer 2 header. Okay, so every one of the layers is going to map or to add more information in order this packet be moved properly in the network. Now here there is something that we have to mention also, that in the previous chapters, in the previous modules, we were talking that MAC addresses for the destination are going to be changed according to the destination end device. So if this end device is inside the network domain, the local area network, the MAC address is going to be discovered by the source end device, and after it will be implemented into the layer 2 header of the packets. But if the destination device is in another local area network, it means that these packets must be transferred through the router, and for this reason the MAC addresses will be changed for destination. So we said that the MAC address is going to be changed to the MAC address of the interface of the default gateway, and after, the router is going to implement the next hop address, MAC address, in this packet. There is something that also we have to mention. This is what we call NAT. It is Network Address Translation. I'm going to explain this later, but anyway, just to give you the idea what is the meaning of Network Address Translation. Today, you know that IP version 4 it almost depletes. It means there is no anymore IP version 4 public addresses free that can be allocated to some end devices. For this reason, in near past, the scientists decided to make some mechanism or technology that can provide more flexibility in distribution of the IP addresses. So the whole range of IP version 4 was divided into two main parts, which one of the parts, like Class C IP addresses, was defined as private IP addresses, and the other range, the other part of the whole range, was defined as public addresses. There is some small part that is used like for science needs or some training or test, but this is a really very small part. Plus, additionally, there is a small range for multicast addressing. So the main idea was that we can use internally in every local area network private addresses of Class C. But when an end device of the local area network wants to send a data outside of the local area network, on the edge router are given some public IP addresses that will be used to provide a transfer of this message from internal device of the local area network to outside. So this transfer from private to public IP addresses is called network address translation. Of course, we are going to discuss this more in later on, but just to give you the idea of this. There are some important characteristics that we have to mention for the Internet Protocol, and these are that IP is connectionless, best effort, and media independent. And we are going to see now what every one of these characteristics mean. Like, connectionless means that this protocol, when it is used, the end devices do not make in advance some connection to provide or to start the session. They actually send their packets without to know that if these packets will reach the destination, or maybe these packets will be lost somewhere. This means that IP is connectionless. Now, also, there is no control information, like, for example, there are no signals for synchronization. There is no sending of packages that they prove the acknowledgement of receiving another packages, etc. Which means that this protocol is some kind simplified in order to provide fast transition of the packets through the network. Maybe you will ask, what is the meaning of synchronization? You know that when we use serial data transfer, there is some signals in parallel that provide the kind of synchronization between the two end devices of the serial interface. Also, TCP protocol, which is in layer 4 that we're going to study in the module 10, uses some kind of handshaking. And in this handshaking, we have some messages that are sent at the beginning of the session to ensure that the device in this conversation is ready, is powered on, is responsible, And to prove this communication, the devices exchange acknowledgements between them. The destination will receive the packet when it arrives, but no pre-notifications are sent, which means that sometimes it is possible for some reason few or more packets to be lost, like for example attenuation on the line or some interruption, etc. So for this reason, if we need to be sure that all packets are sent and received by the destination, are sent to the destination and received by it, there are some protocols that from upper layer can prove this reliability or this the complete received message. What do I mean? One of the examples is that using TCP protocol in the layer 4, or probably there are some applications that also can provide some kind of control and requesting of repetition of the some of the packets that are not received. And here on this slide, you can see a very simple picture about this. If somebody writes a letter, this is an old-fashioned way of writing letters, he put in the mailbox facing the house, but after this, he doesn't know that this letter is going to reach the destination or no. The way of the letter is that the mailman comes to take the letter, put it in a truck, and after it goes to the post office where the letters are distributed according to the addresses, and after this another truck distributes the letters to the right addresses. So this actually what we mean of connectionless. Best effort. What is the meaning of a best effort? There is no guarantee that the packets will be delivered to the destination. This is the meaning of the best effort. The infrastructure, the intermediary devices, they work properly. They just take decision how to forward the packets, but they cannot guarantee that these packets will reach the right destination. So if we have to say in general that almost the packets, if they're configured and they are created correctly, if there is no any problem on the line or some interruption or some heavy traffic congestion, the packets for sure will reach the destination. Why do we have to do this? Can you imagine if we have all these packets, different devices send simultaneously their messages to different destinations, and we have so many devices. If we have to provide some kind of control, sending back acknowledgement packets for each one of the IP packets, it will be really enormous additional traffic on the line, which will make delays and will reduce the user bandwidth on the network. So for this reason, we have to reduce all this overhead traffic and to provide some easier transmission without additional control packages for acknowledgement. So IP does not expect acknowledgements, it doesn't use acknowledgements, and this is for the reason that we want to reduce the overhead traffic. What is about the third characteristic, the media independent? Now on this picture you can see that if one end device wants to send a message to a far remote device, this message could pass in different links, in different connections following different media. Like for example, here we have Ethernet connection following by the serial. Here we have optical, fiber optic, Also, we have wireless, and all this is, as you know, part or question of data link layer, layer 2. That's why we say that IP, the network layer, is independent of the media. It doesn't care where the packet has to pass unless the routers that are implemented in this path know how to take decision and to forward the packet to the destination. Now, there is something that we have to discuss also. This is what we call maximum transmission unit. Maximum transmission unit is actually the data payload that can be implemented in the packet, including the packet header, which means that if, let's say, for IPv4 and for Ethernet frames, we can have data payload up to 1,518 bytes. Some of older devices and somewhere that we have a lower bandwidth, lower like copper links, but with lower speed, for example, let's say we have 100 megabit per second, we probably will have some bottleneck, which means congestion, a lot of traffic, slow, low speed, and this can provide some significant delays in the communications. What usually we can do in this way, we can provide some change in the MTU, the maximum transmission unit. This is controlled by the data link layer, as I said. For example, here we don't have all intermediary devices powerful and fast working. Some of them, let's say, probably are old and they cannot handle high speeds. That's why, in order to provide proper movement of the traffic, we are going to change the MTU. When you reduce the MTU, let's say from 1,518, we reduce it to, let's say, 512, it means that you have to provide some fragmentation of the data payload. Yani we divide into parts, in equal parts. In this case, we reduce MTU and we provide kind of fragmentation. That is also an issue of the IP protocol. And after a while, we are going to discuss what is exactly the fragmentation. So for now, you have to say that the fragmentation splits the IPv4 packet into smaller equal size units. Of course, this is dictated by the devices in the data link layer, and also it can be controlled by the operating system of these devices. Now, in general, because this is an additional processing, we have to say that the fragmentation can bring latency, but this is normal because we talk about older devices that are slow or in their processing, the speeds are lower, and for sure we can sense latency in the communications. Now we are going to discuss the header of the IPv4 packet. Now, first of all, we are going to say to discuss about the what exactly these packets contain. As I said at the beginning, the header of the IP encapsulation contains the source and destination IP addresses for each packet. There are some more fields that we are going also to discuss. And using this information, the routers that receive such packets can take right decision where to forward the packets in order to reach the destination. Now here what you see is the header of the IP version 4 packet. Altogether there are 20 bytes, and on this side the width of the fields is given also in bytes. So you can imagine, of course this is not two-dimension, you can imagine that each line, I mean this line follows the first one, the third follows the second one, and so on. So the header of the IP version 4 starts with the field of version, which is the version 4. It means that the routers today, most of the routers that we have can operate in the both versions, version 4 and version 6. But because the IP addresses that will be implemented here downward, the source and destination IP addresses, they are written in some format. That's why we have to give first information about the version of the protocol. Here supposed to be 100 in binary code for number 4. Next field is the internet header length, which is about how many bytes we have in the header before the data payload. After this, we have another fields that will provide the so-called differentiated services. DS, differentiated services, it means that here we have some options about what is the type of the data payload that follows this header. In the past, they were talking about quality of services, which is almost the same. Here we can say that this can indicate what is the type of data. Is it regular data, or if it is voice or video signal? So in 1 byte, we can provide this specification. There is also some code point, DSCP, which is not part of the CCNA1. And also we have 3-bit for so-called explicit congestion notification, which means that if these bits are set, they indicate explicit congestion notifications. Here we have some options. Where is this explicit congestion? It is probably from the direction from source to destination, or from destination to source, which is upload and download. So in case we have this indication, it means that we have to slow down the sending of packets, and the following by some fragmentation of the data payload. Total length is actually in bytes the length of the whole packet, including the header and the data payload. Now here about the next fields we have so-called identification, which means that if we have to provide fragmentation, let's say in one message we have, let's say, 20 packets. Each packet has a number in order to provide the sequence when these numbers will be used in the destination to arrange the packets and to create the whole, to combine the whole message. So let's say we have to provide fragmentation of packet 1. I simplify the numbers, they are for sure much more complicated, but packet 1, when it is fragmented, all fragments will have the same number of 1. So this is what we call identification. It means that in this field we are going to have the same number of all fragments of a packet. Next one is the flag, which means it indicates that there is a fragmentation, and fragment offset will provide actually the exact position of the fragment in the original packet. There is one field, time to leave. What is the meaning of that? Usually time to leave is set by the operating system, and almost for the IP version 4 it is 15, which means that every time a packet passes through a router, that we call it a hop, time to leave value will be decreased by 1. It means that if this packet cannot reach the destination, it will be rounded by different routers. Time to leave finally will reach 0. So when insert in the next router it reaches 0, it means that the router will drop the packet. It is not going to forward it anywhere. Actually, the field helps devices to drop a packet that cannot be sent to a proper destination. In this way, we can reduce the traffic of some undesirable or not complete packets. The protocol field shows what is the protocol in the higher layers, which means what is implemented in the data payload here in this gray field. And there is a header checksum, which provides some value that is obtained by an algorithm taking all this information from the header and implemented in the field. When this packet reaches the destination, the same algorithm will be implemented by the operating system, and when the end device produces the checksum, it is going to compare with the checksum of the this value that is implemented in the header. If these two sums are the same or there is matching, it means that everything is correct. There is no altering of the information, and this packet is received properly. So finally, we have the source and destination IP addresses that we are talking about, that for IP version 4, you know that each address is of 32 bits. And here also we have some description about this. The differentiated services, as I said, is for quality of services, or like what we have types of services. Here, time to leave, as I said, we have the hop count, etc. Now, what is the situation with the packets and their headers in IP version 6? First of all, let's discuss why do we have to go for IP version 6. As I said, 32 bits in the address can bring us 2 to the power 32 different unique IP addresses. Today we have a vast number of devices that tend to be part of the network and internet, including desktops, laptops, different devices like tablets, and any other models that can be implemented in or can use the internet. So each one cannot pretend to has a unique IP address. If it doesn't have an IP address, it cannot be part of the network. So what is going with IP version 4? Lately, the scientists said that the whole range of IP addresses will not be enough to cover all devices that are in the internet. That's why they decided to make extension of the IP addresses from 32 to 128 bits. If you calculate 2 to the power 128, you are going to receive a very huge number of IP addresses. And here you can see this clear. The use of IP version 4 can bring us around 4 billion addresses. But using 122, we talk about some another unit, what we call it, undecillion, which look how many zeros there are. It is a very huge range of IP addresses that cannot be covered easily. There is an advantage of using this large range of IP addresses, and especially when we talk about NAT, Network Address Translation, and about PAT, which is Port Address Translation, which means that in this way, using IP version 6, plus additionally newer devices that are more powerful, faster, with higher or greater capacity in the main memory, more powerful CPUs inside, and improved operating systems, the work with IP version 6 is much better and easier. And plus, we don't need to define private addresses and public. Actually, we can work freely with different addresses on the device. And in IP version 6, I want to tell you that one device can have more than one address. This is the header of IP version 6 packet. And as you see here, even though that we have much larger, 4 times greater in bits IP addresses, the header is simplified. We have only few fields. Some of them are the same like in IP version 4 header, and some of them are new. So here we can see that this header is limited to 40 bytes. And some of the new fields are flow label, we have next header. The source and destination IP addresses, as I said, each one is of 128 bits. The first field is the version. It is normally to say that here the field contains 110, which stands for 6. The traffic class corresponds to the differentiated services that we have in IP version 4. Now here we have another new field that is called flow label. And usually the flow label contains a number that indicates all packets of one conversation, which means that these packets belong to the same message, belong to the same conversation, and never mind when they are forwarded, finally when they reach a destination, they will be with the same number, with the same identification number, what we call it flow label. The payload length is actually the number of bytes in the payload, data payload that follows the header. And here we have something very interesting, what we call it next header. Next header is actually a field that contains more information needed for the to be included in the header if the data payload is specific or comes from an application that requires more details. So here, this header that you see is simple and is mainly for the packets that contain ordinary data, simple data. But if you have some applications that require more information, of course, you are going to use the next header. Otherwise, the next header will be empty. Hop limit is the same like time to live in IP version 4. Okay, so I wanted to show you what is the meaning of this next header. Like here, the description is that we can have some additional information about the protocols in the upper layer, like ICMP, TCP, UDP. TCP and UDP, they are of layer 4. Internet Control Message Protocol, ICMP, is a protocol that is used in IP version 6 for many reasons. We're going to discuss this. And also it is used in the IP version 4. In IP version 6 is ICMP v6. So here I put some illustration of this, what we mean about next header. Usually this is the simple header that you have seen in the previous slide. And in the next header, we have some additional information that leads to extension header. In this extension header, we have information like, for example, about TCP, ICMP, etc. And if you need more information, you are going to find out that we have another next header in this one that will lead to another extension header. Actually, the operating system allows up to fixed n, which is somewhere n is equal to 8 or 16. And according to this, we can implement many other information fields, including security also, etc. So all this here, what you see, can be extension of the IP version 6 header, the original one that we have seen before. Here, what we have is the data payload that comes from the upper layers. So as we said, all this information can be used for different reasons, for security, for mobility support, for mobile fragmentation, etc. Now we are going to discuss how these packets are processed and forwarded by the routers. First of all, we're going to discuss something about the end devices. This is what we have here in the picture, like PC1. There are two options that we have to discuss. The first one is if this PC1 wants to send data to some device like PC2 that is in the same domain. There is a difference if PC1 wants to send a data that is to device, directed to device that is outside the domain. It means that this device is in another local area network, like what you see here, the server. So here in this situation, as you see, the packets must be transmitted through the router R1. How PC1 is going to send the packets to the other end devices? First of all, we want to say that internally, the operating system of the computers has some information that concerns the device itself. Like everyone, computer has its own IP address, the IP address which is the local IP address 127.0.0.1 for IP version 4, and this 4.1 for IP version 6. So here we have to discuss the situation how the packets will be sent to the local hosts that are in the same domain and remote hosts that are on a different LAN. So if you have IP version 4, the source uses its own IP address and subnet mask along with the destination IP address. Now, this is for the layer 3. For IP version 6, the source uses the network address and the prefix advertised by the local address. Now, I want to tell you that according to the new distribution, this is, as I said, a new version of CCNA series of courses. The discussion of IP version 6 is in the following modules. So probably you will find some missing of information, but anyway, the prefix stands for the portion of the IP address that concerns the network address. If we want to send traffic to a local host, we are going to use only the IP address of the local host and with the combination with its MAC address to complete the frame. But if we have to go for sending packages to remote host, we are going to forward these packets to the default gateway, which is the interface that connects to this local area network, and the interface belongs to the intermediate device router R1. Now, about the default gateway. You know that this is usually additional IP address that is available in the configuration of the end devices. And this is very important information if the device wants to communicate with remote devices from different local area networks. So the features of the default gateway. First of all, it must have an IP address that is of the same local area network. Let me see here if we have this one. Yeah, look at this. Here, the local area network is with an address 192.168.10/24, which means that the first 24 bits from here to here, these first 3 octets, what we call, is the network address. The last octet, which is 0 for the network address, for each one of the devices will be given a unique number, which is, because we talk about octet, yani here we have 8 bits, 2 to the power 8 gives 256 possible addresses. But because the first one, the 0, is for the network itself, and the last one, 255, is the broadcast address, actually, the real addresses that could be given to the devices are 254. As you see here, PC1 takes number 10 and PC2 takes the number 15. Number 1 is given to the default gateway, which means that this interface is a part of this local area network. By this way, the devices can communicate to outside, redirecting their packets to the default gateway. From here, the router is going to take decision when it finds out after the encapsulation the destination IP address, and looking in its routing table inside, will search for an entry that will match the IP address of the destination. When it finds a matching entry, it will use the exit address of interface and will send to destination. So finally, if we don't configure the default gateway on end devices, we are not going to provide proper communication of these devices to outside of the local area network. So here, in this example, also we have the same picture. If we use IP version 4, it means that here on these devices we can put manually configuration of their IP addresses and the default gateway. You know this in the Windows operating system, how to do. This is actually the use of how to configure manually. But today, we more frequently use DHCP server, which is actually dynamic host configuration protocol. And the DHCP server is a device that is somewhere in the local area network, and it is configured with the range of IP addresses. Let's say what we have here, it's supposed to be 254 different IP addresses. And every one of the devices, when it is powered on, will send a request to the DHCP server for gaining dynamically an IP version 4 address. DHCP server will lease an IP address, free IP address to the device, and it will be for certain time. Let's say, for example, 24 hours or 1 week or 1 month. It depends on the configuration in the DHCP server. After this, the device can use this address for the least period of time. For IP version 6, there is a little bit different communications. Usually the devices provide some sending of packets that we call solicitation packets, and by advertising, the router is going to send IP version 6 addresses to the end devices. We have the last two slides of this module discussing the issue. Now, look at this. Every one device, including the computers, have so-called routing table. In this routing table, like for example in the slide here, if you issue netstat space -r and you click enter, you are going to see the routing table in your device in this moment. The routing table is a kind of complex or set of entries that some of them are static. They cannot change, like what you see here, the first few entries. And also we have some dynamic entries that are given, like for example, this number IP address is given, let's say, from the DHCP server, and it is going to be for some time. Also, we have here some multicast addresses implemented, and these are the broadcast addresses. So this is actually information that the computer keeps in its main memory in order to communicate on the network. There is another command here, route print, also that will give you more information in three parts. The first one will be about the interface list. After, you are going to see the IP version 4 routing table, and finally IP version 6 routing table. Now, what is going to be if, let's say, a PC1 wants to send a packet to PC2 that is on another network? Look what we have here. On this side, we have network 192.168.10.0 that is connected to interface G000 on R1. From the other side, the other interface of R1, G001, is connected directly to R2, and they are in a network 209.165.200.224. Look, this is direct connection, so we are going to change the subnet mask to 30, which means the network address is 224, and the two interfaces have the addresses 225 and 226. 227 will be a broadcast for the network here, so the two routers can exchange broadcastly some information when it comes for broadcast messages. After R2, we have another LAN, which is 10.1.1.0, and here we have PC2, which is a destination of the messages that PC1 wants to send. Now, I'm going to remind you again, if there is some communication using a remote destination device, the MAC addresses will be changed a few times here. Why? Because MAC address works in layer 2. R1 and R2 are layer 3 devices. They work with IP addresses. They do not work with MAC addresses. That's why when we have to implement MAC addresses in the frame, PC1, first of all, will put his own MAC address as the source MAC address, the destination after, when R1 works to forward the packet, the destination in the, through 3 steps, 1, 2, 3, is the same, 10.1.1.10, which is the PC2 address. The source IP address is the IP address of PC1, and it is going to be the same because the PC2 wants to know who sends the message and to reply eventually. But the change is going to be in the MAC addresses. Here, the MAC address will be changed to the MAC address of the interface G001. Destination MAC address is going to be of the interface here to 226, G001 probably, or 00, and etc. So finally, the MAC address in the last part of the messaging is going to be implemented of the MAC address of the network card of PC2. This is about the addresses, but what is going to be inside the R1 and R2 as processing to making decision where the packet from PC1 must be forwarded to. So R1 and R2, they have their routing tables. They have, like here in the example, they have some entries in the routing table. Of course, this is much more simplified. We're going to see a real routing table later on, which means that for every one known network, the router must have some decision or exit interface. Like, for example, in R1 routing table, for the destination network 10.1.1.0, the direction is via R2, which means to R2. Also, R2, when it receives this packet, is going to search for 10.1.1.0, and it will find that this is directly connected network to this interface .1. So it will encapsulate the packet with the new MAC addresses and will forward it to the switch and further to PC2. Do you have some questions? I don't know if everything is clear. Nobody answered. Okay, so about the routing table, there are three types of routes that can be recognized in the routing table of a router. We have directly connected, we have remote, and we have default routes. Now here, about R1, we have two networks that are directly connected. So these routes are clear. 192.168.10.0, all devices of this network are directly connected to the interface 1 in R1, and also this network is directly connected. So very quickly the router can learn this information and put it in the routing table. But the router doesn't know anything about the remote network, which is 10.1.2.0. For this reason, R2 must give some information to R1 about this directly connected network to R2. And it has one and probably we have something here to provide information for 10.1.2.0 to R1, and also we have to provide information for 192.168.10.0 network for R2, because this network is not directly connected to R2, it is a remote network. And there is finally default route that is used to provide direction for some networks that are not known by the routers in this time. So let's say there is some packet that comes here from PC1 to R1, and it doesn't have any information about the network. Let's say we have a network 10.2.2.0. Here is 10.1.2, so it's not the same. R1, if it has default route, which is 4 zeros, will use it, and it will be probably here redirected to R2 and to the internet. All this we're going to discuss later when we start the routing tables in details, but now you have to have the idea about these three types of routes that can be seen in the routing table of each router. There is something that we have to say about the remote networks. How can we configure these remote networks on the router? We have two ways. First of all, the statically or manually writing the routes. Like what you see here, we have R1 in the global configuration mode. We have IP route command, and we with the subnet mask and address, which is 209.165.200.226. Okay, this is the IP address of the next hop router. Well, it's okay. This is just fine if we have simple configuration like what we have here. But can you imagine if we have many routers and we have many networks, many subnets here, and we have to provide all statically, or just to provide manual configuration. We go to every router and we have to provide all configuration of all remote networks. This is impossible. It will bring a lot of errors. And for this reason, we have so-called dynamic configuration. Dynamic configuration usually is using the dynamic routing protocols like EIGRP, OSPF, and any others that can be configured in each router. And from there, the routers can communicate dynamically for any change that happens on the network. Like for example, here, if you have a static route, and this static route is configured between R1 and R2, in order to connect to 10.1.2.0, if this static route fails for some reason, the connection here fails, the router R1 will not know that it could provide this information through R3. But if you have dynamically configured R1, R2, and R3, it will be easier for R1 to change the path from R1, R2 and the network to be like R1, R3, R2, and this network. So only using and lose the connectivity. Dynamic routing, as I said, is using two main protocols like OSPF, open shortest path first, and we have another one, EIGRP, which is also very powerful and used by routers. Actually, these protocols, they are available in the operating systems of the routers, which means that if you want to choose OSPF, you have to configure R1 with OSPF and also R2 with the same protocol. If you configure R1 OSPF, R2 EIGRP, it will not be possible these two routers to communicate with each other. Also, we have lessons about these modules that you will know how to configure the routers using the dynamic routing protocols. And now here you can see an example of a routing table, let's say of router R1. So if you use the command line interface and you issue in the privilege mode show IP route, you are going to receive this output, which is very helpful to know how the router can provide routing, and you can see if all networks are available here in their entries. So we issue show IP route, and you see here we have a long list of different signs that can give you information about different protocols and for example, if you have EIGRP protocol that R1 is configured, you are going to see some of the entries with letter boxes, or for this network 10.1.1.0 is for OSPF. Here you can see that O stands for OSPF. Also, 192.168.10.0 is subnetted. Here we're going to talk about subnetting later on. And here we have two subnets, 192.168.10.0 and 192.168.10.1. Here it's not seen the second one, but probably is somewhere here. Anyway, it's an example just to show you what routing table looks like. Now, about these entries, you see that everyone is directly connected with C, and we have one local or logic connection that is concerning the router interface itself. Like for example, this one, 192.168.10.0, the interface is 1. So next is 192.168.10.1. Look, the subnet is 32, which means that this is the interface itself. This option appeared in operating system of the routers, the version 15, which is one of the latest versions, and it is mainly for easier addressing of a traffic that is for the router itself. It's not for end devices. And for example, if these two routers R1 and R2 are configured in OSPF, protocol exchange traffic is very helpful to show directly IP address. Directly connected is 209.165.200.224, this network, and the IP address of the interface is 225 with this /32. يعني هيدي معناتها /32 معناتها the address of the interface that is on the router itself. And as I said, it is only for the exchange traffic between the routers. And this traffic is not going to be sent to end device. Now, there is something that also is important, the static route with S, and there is some star which is candidate default. In هيدي معناتها إذا نحن we don't, or R1, if he doesn't know some packet where to send, لأنه ما في عنده أي matching of these entries, this R1 is going to use this default route, which is via 209.165.200.226. يعني معناتها راح يبعت كل هيدي ترافيك على R2. R2 probably has a static route that is going to internet, and it will forward this traffic to from this interface. So this is actually very helpful for all packets that are not known or they do not have entries in the routing table. And you know that it is the routing table is limited space. It cannot be used to cover every possible LAN address because it is a very huge set of LANs everywhere in the world. So this is actually helping to exit and to provide these packets to some another area in the. I will go for the next module 9. Do you have any questions, guys? Well, module 9 is about addressing we're going to discuss also MAC and IP. So the destination device is in the same network. It means that when PC1 wants to send a message to PC2, this message must pass only through the switch. Now, when the two devices are powered on, the switch learns that on specific port, let's say 01, is connected the device 192.168.10.10. Of course, it doesn't have information about this IP address. It will take the MAC address of the network card. and it will save it in its switch table, MAC address table. From the other side, it has information that on the other port, let's say 02, has connected PC2 with MAC address 5555, etc. They are simplified here. You know that the MAC addresses are up to 48 bits, which means that these addresses are implemented in the in the MAC address table, and they correspond to ports. When PC1 wants to send to PC2, it knows that the IP address of PC2.
شايفين شيء؟
Yes. نعم.
عامل شير سكرين بدي شيء؟
ما بتشوفوا؟
لا مش شايفين.
Okay, just a moment. Now do you see? عم بتشوفوا هلا؟
Yes, doctor. Now we can see.
Type, okay. Oh, thank you for telling me because. Okay, so I'll repeat. Halla, we have to discuss how we have, what is the relation between the IP addresses and the MAC addresses. And here we have discussion on a local area network in one domain. Yani between the end devices, في عنا only the switch, which is layer 2 switch, and all domain is network with the address 192.168.10.0. هلا, when PC1 wants to send frames or packets to PC2, أكيد انتوا بتعرفوا they have to have the same application, working with the same application to exchange their messages. So going down Aussie model, when PC1 wants to send the message from the application, it will be encapsulated into IP header أول شيء. راح يتدخل هون 192.168.10.10 as a source IP address, وأكيد لازم يعرف the 192.168.10.11 of PC2. Now, if PC1 doesn't know what is the in order to implement additional MAC header or provide information for the MAC address of PC2 and to put it into the header, like what we have here. How it is going to be done? PC1 will send address resolution protocol request, and this message will be broadcasted. بهيدي message راح يكون في عنده questioning. What is the MAC address of device with IP address 192.168.10.11? This is going to be broadcasted by the switch to all directly connected devices without the origin. And كل واحد من devices, let's say إذا في عنا أكتر computers here, everyone will receive the message, will encapsulate, and will see that there is a question about the MAC address of 192.168.10.11. The others will drop the message, لأنه they have different IP addresses. Only this one, PC2, will reply to PC1 and will send that my MAC address is this one. It will be sent unicast to PC1 because in the message, PC2 will find the IP address of 192.168.10.10. كمان راح يعرف his MAC address. So it is going to send directly unicastly to PC1 this information. When PC1 knows the MAC address of the PC2, it can complete the data link header, will put destination, the MAC address of PC2, will put source, MAC address, the destination, the IP address of PC2. This is about the local area network, but not every time this case is seen. Some more frequently, we have exchange of data between end devices of different local area networks. So let's see how it is going to be done. When we have this situation, like PC1 wants to send data to PC2, and it knows the IP address of PC2, what is going to be produced? We said that the MAC addresses will be changed, which means PC1 will use as a destination MAC address the default gateway MAC address, because it will know that the IP address of PC1 and IP address of PC2 are not on the same network. The source is 192.168.10.10 and destination is 10.1.1.10. It means that there is no matching, and because there is no matching, PC1 will know that this end device is on another network. It is going to send this message to the default gateway. So as a destination, it will take the default gateway of interface that is here connecting this local area network. After, when the packet comes here on R1, is received by R1, R1 will look up and it will encapsulate, will take event, and we'll see that the source is part of this network and destination is another address that is in a remote. So in this case, what is going to be done? R1 will look up in the routing table, will find out that to reach 10.1.1.10 is part of this network, and it is going to forward it to this interface, G001. So what is going to be in the headers? The same IP addresses, the source MAC address is the same, but the destination MAC address will be changed from this one to DDDD, okay? Because this is the destination MAC address for this moment. And R1 is going to send to forward the packet to R2. Because it knows the routing table that to reach this IP address, it must go to 209.165.200.226. When the packet comes to R2, R2 will de-encapsulate the data link data and will find that the destination is 10.1.1.10, which is directly connected network. It is going to forward the packet to this interface G000, and in case it will be will keep the source MAC address, will keep the source IP address and the destination IP address. Only the destination MAC address will be changed to what? Will be changed to the MAC address of the PC2. Okay, when PC2 wants to return the information, what shall PC2 implement in the MAC address? In the source will be this is home, and the destination will be address of G000. When it processes the packet, will MAC address the MAC address of G001 of R1, because it knows that the destination MAC address, the destination network is 192.168.10.0, which is remote network for R2. And after this, R1 will receive the packet. Of course, here the source and destination IP addresses will be exchanged. Now the destination is this one, and the source supposed to be PC2 because it returns or replies to the first message of PC1. So R1 will receive the packet because destination MAC address is this one, CCC on G001. It will proceed and it will find that destination IP address is of directly connected network 192.168.10.0. So R2, now it will know that PC1 is part of this network, and in the destination MAC address we'll put the MAC address of PC1. About the IP version 6, the situation is easier because, as I said, there we use some specific messages about IPv6 salutations and IPv6 advertising, and we're going to see also such situation to discuss. Okay, so I mentioned address resolution protocol. Address resolution protocol, it means that if device has an IP address of the destination and it doesn't have a MAC address of the destination, using ARP request, it can get the MAC address of the destination. So here we have the main reason to use ARP is to obtain the destination MAC address of. We have two basic functions that ARP can provide to resolve IP version 4 addresses to MAC addresses, and also to obtain the ARP table to MAC address mappings, and of course to corresponding IP version 4 addresses. So here we have this situation. This computer wants to send some message to a computer H4, which is on the same local area network, but it doesn't know the MAC address of this device. Now, in this situation, H1 will send ARP request message, which is broadcast, yani بالMAC address destination راح يكون في عنا all ones, and inside the message the data payload راح يكون I need to send information to 192.168.1.7, but I don't know the MAC address of the device that has that IP. And it will be sent to all devices. Now, devices like H3 and H2 will find out that their IP addresses do not match this address 192.168.1. So they will discard or drop the packet. Only H4 that will find its IP address is the same like in the message will reply, will return, but now not broadcasted. It will be and message it will say its MAC address. So this is used in local area network. About ARP functions, we have to say that the ARP provides ARP table that is going to be temporarily modified, or some of the entries will be deleted. Usually there is a timer, ARP timer, that can be defined by the operating system of the device. It could be like around 45 seconds to 1 minute, or probably more if it's required. But actually this entry will exist for the time that the messaging is going to this device. Okay. Here is an example. So there is some communication between computer A and computer C. Now, there is something like, I will remove this ARP entry if I have not used it in 2 minutes. Of course, this timer, when the last message or the last packet is sent to the destination with such MAC address, it is going to be, the timer is going to starts, and when it reaches the predefined time, and there is no during this time any other packet sent to the destination, this timer will provide a delete of the entry from the ARP table. ARP table or cache, what we said, is going in this way. We have IP address and corresponding to it. In time, this entry is automatically deleted from the ARP cache table. Now we have some commands that we have to know. Show IP ARP. This is a command that every time we are going to use in the routers, that will help us. To provide information about the current entries in the R1. Which means show IP ARP. In this example, we have only the address 192.168.10.1, which is defined by the Ethernet protocol. Now here we don't have exactly timing. We have hardware address, which is the MAC address of this device. And here we have type ARPA, which is specifically for the protocol, Ethernet protocol 802.3, and also the interface that is connected to the network card of this device. Okay, so this is the information. If you have Windows 10 on the PC, we can use for command ARP space -A, which is actually a command that will give you the MAC addresses corresponding to the IP addresses in this moment. And here we have dynamic entries. It means that in this time, this computer that we provide the command on it works or was connected with two different devices, like what we have here, 192.168.1.1 and 101. Their MAC addresses and as I said, deleted from the table. there is something that we have to take under consideration if we talk about the security. لأنه when the end devices want to discover the MAC addresses, they usually send ARP request broadcasting. يعني معناتها all connected to the domain devices or connected to the switch could receive this broadcast message or ARP request. If in this time there is some intruder or attacker or hacker connecting his device, this especially goes for wireless connections, but anyway, it could be also wired. This hacker can receive also the ARP request. It can simulate that it has the existing IP address and will return his own MAC address to the requesting device. So now the requesting device is going to send all information to this hacker. So for this reason, we have to provide some security techniques that will eliminate the use of another unknown end devices on the network. And this is what we call dynamic ARP inspection. Dynamic ARP inspection is not part of CCNA 1, but the idea is that we previously know the MAC addresses of the known end devices in our, and we don't any other new MAC addresses. This is usually configuration on the switch. So if on ports there is some device connecting like this, the switch will use dynamic ARP inspection. We'll find out that the MAC address of the network card of this device is not available in the list of well-known MAC addresses, and it will power off this port, so nothing is going to be sent to this hacker. About IP version 6. Here we have, as I said, some differences leading the protocol IPv6, where the devices in a domain can provide sending some messages using the NDP neighbor discovery protocol. The neighbor discovery protocol provides the messages that we have neighbor solicitation and neighbor advertisement. Additionally, we have address resolution, router discovery, and redirection services. Address resolution is when a new device connects to IPv6 domain, it will send neighbor solicitation to get the addresses that are part of this domain, okay? And neighbor advertisement is actually the reply to the neighbor solicitation, and they include the addresses that will be given to the required device. Also, there are these messages can be sent between the neighbor routers. So, using the redirection service are used by ICMP version 6 protocol to provide redirection if the router considers that there is some problem of a link, or it wants to provide some balancing in the traffic. So this is another. Now here you have some simple demonstration of this. Let's say a PC1 sent a neighbor solicitation to provide a MAC address, to take the MAC address of PC2. It will write like, hey, hi, whoever has 2001 DB8 ACAD 111, send me your MAC address. Of course, in all this domain, with this prefix 2001 DB8 ACAD 2.1, this is actually the network address in IPv6. And after the 4 points stand for the other part, which is concerns the additional addresses of these end devices. So when this message is sent, PC2 will find out that it concerns its IP address. So it is going to respond by the neighbor advertisement, and it will send its MAC address to PC1. After this, PC1 can formulate or can create the frames and send its messages to PC2. Okay, so this is for today about the modules. I want to tell you guys that we have to make some of 4th of January, which is the next session. We have to make the first module. Here, let me show you. Do you see the screen or no? Maybe no. Well, my screen. Now, do you see the screen? Guys, can you answer me? Do you see the screen?
Yeah, yes, doctor, we can see the screen.
Okay, so look at this. We have module 1.3, which is about the first 3 chapters, 1, 2, and 3. I will ask you to read these chapters, and I will send you by email the time when the exam will be activated. I'm going to activate it for, let's say, for 2 days, yani the January 2nd and 3rd. Okay, so you can do this exam anytime in this period, yani 2nd and 3rd. Okay, you have enough time. So you have the questions. There are around 70 questions. They are taken from the material. And this is just to provide your preparation for the first 3 modules, okay? You're going to take a grade, so it will be also available in the academy. For the students that didn't make the exam, they are not going to take grade, so they will see 0 in their grade book, okay? So this is really important. As I said, I'm going to send an email about the activation time.
Doctor, just a
Yes.
question.
Yes.
Do we need packet tracer for the exam? Because I don't have my computer right now.
Well, I don't know. I'm not sure if it was available packet tracer inside, but if there is, there are probably a few questions, maybe 2, 3 questions maximum. Maybe no, I'm not sure. Because I didn't look at the questions. But anyway, I just wanted to also to tell you about the packet tracer. Probably we don't have time so much, but anyway, I'm not going to be, will take a lot of time. So this is about the exam that is going to be before يعني قانون تاني, okay? عارفة كنون تاني هيدي شيء يكون واضح. لازم يكون كلكم تعملوا هيدي امتحان. Okay. Is there a question or what? I also don't have my computer, so I use another one, and I'm a little bit confused. This is about the exam, guys. Let me show you now about the packet tracer that I wanted to. I wanted from you to do some exercising, which is good to know. First of all, how to work in the packet tracer, and this is 913 packet tracer موجود بالclass materials. Okay, so you can see it here. No. Anyway, it's موجود بالclass materials 913. Let me show you some. What do I mean? What to do? Well, this packet tracer will not be graded. Actually, there is everything available. بس انتوا شو لازم تعملوا? You have to provide some research to see how to identify MAC and IP addresses. So this what you see here is everything is ready, everything is configured. You see the green triangles معناتها في عندنا connectivity. Also we have here addressing of the computers. They are in two different LANs. هيدي LAN with 10.10.10.0. The 2 and 3 are unique addresses for the two computers wirelessly. On the other side, we have another LAN 172.16.31, and the computers are given addresses 2, 3, 4, and 5. I wanted to provide. Okay. I wanted to provide some information for you how to work. Look at this. We have some simulation. This simulation mode can bring us the way how the messages are sent between the devices. Now, the first one here, we don't have anything. I want to provide filters. Here we have ICMP. So I click here, edit filters. I can choose which protocols packet I want to see. I'm going to put ARP, and also I have ICMP. I close. And now I want to, let's say, I'm going to choose 172.16.31.5. To make some request to 172.16.31.2 by ping, okay? So here with desktop, command prompt, I have ping, and I will take this 172.16.31.2, 16.31.2. Enter, and now here we have, look how the packets are going. In the same time, you can see on this side, you can see every packet, where is the, with what time, the device, the destination, and what is the protocol used. So if I use, let's say, from 172.16.31.3, no, I want 2, and I click here on the green, I can see exactly what is the MAC address for this device. And as you see here, I see the OSI model. OSI model in the layers. And here, this ARP works in the layer 2. Okay, layer 3 I don't use now because I didn't choose the filter. If I use here the filter for, let's say, IP address, كمان I'm going to see here layer 3 with the IP addresses. Now, as you see here, the two protocols, because we choose only two filters, we want to see the packets of ARP and ICMP, they are given in different color. ICMP is in this yellow, ARP is in the green. So here it is really very nice to see how the traffic goes between the devices and to follow the different packets of different protocols, how they reach the devices. So this is about the layers. About inbound PDU also some information, but this I'm going to discuss with you later on when we talk about PDUs in details. Okay. So this is what I want you to see in this packet tracer exercise. 913 is available in the team group. You can download from there. Also is available in the course. So if you read the course, you're going to take it from there directly. So it is up to you which one you want to continue. Now I'm going to reset the simulation. Going to the real time. Yes.
دكتور بس كرمال الاساينمنت اللي كان عنا اياه هيديك المره، لايمتى عنا اياه؟ لايمتى فينا نقدمها؟
جايز انا قلت لكم هيدي الاساينمنت كان بس ل في ديت I don't remember هلا ديت، بس كان في وقت معين، فانتوا كان لازم تقدموا بهيدي وقت. كل الناس اللي قدموا بعدين ما في عندهم grades لانه they are يعني exceeding due period. اوكي، يعني صارت الموضوع يعني بوقت معين، ما فينا نعمل يعني extending بالوقت كتير. that's why هيدي راح يكون يعني أكتر من طلاب راح يشوفوا زيرو بالجريدنج بوك. بس طبعا نحن راح يكون في عنا مور باكيت تريسر بالجانيوري، بس نرجع على الشغل على الدارس وهيك، يعني راح يكون في عنا أكتر. so انتوا بدكم تلتزموا بهيدي وقت وبتعملوا هيدي باكيت تريسر، بتعملوا ابلود and that's it. كان في ناس عاملين ابلود بس لل one باكيت تريسر، عاملين كل شيء، بس لانه there are two labs كان لازم يعملوا اثنين مع بعضهم وبعدين يعملوا submit على assignment. so once they make submit.
بس
نعم.
انا حكيتك وحطيت لك اياه على التيمز، رجعت لتاني
نعم
مرة.
نعم that's why أنا بقول يعني الشباب اللي يعملوا بس upload لواحد assignment and it was correct عم نعتبر يعني هيدي great for both. وأنا شفت كمان عاملين بتيمز بعتوا لي إياه كمان صح. so you have the grade for both. طيب أنا شباب I can understand يعني it's new practice لإلكم. so مش مشكلة إذا واحد ما قادر يعمل كل شيء الوقت، يعني بنرجع بنعمل إشي تاني كمان وراح يكون better for you. أنا بس بدي منكم تفتحوا الكورس study from there. في كمان فيديوز كتير حلوين، يعني مثلا للشباب اللي عندهم French basic education راح يساعد كتير هيدي الفيديوز لكل شيء، ل ARP لل routing. في عنا فيديوز بالكورس بالأكاديمي. so please do your time now. هلا بعتقد ما في عندكم كتير ضغط بالدرس and work on Cisco. it is really very helpful. راح تساعدكم بعدين وبالامتحانات كمان بفاينل exams. okay, do you have any questions؟
دكتور كرمال الكويز كمان
نعم.
مطلوب منك كل الموديولز ولا في شيء محدد؟
yes الموديولز مطلوبين، راح يبينوا الجريدز، كل شيء هيدي مطلوب وراح تساعدكم بهيدي بالpreparation of the final exams. so هيدي شغلات هيدي اللي quizzes are really important for you.
يعني كل شيء مطلوب دكتور؟
ايه طبعا.
اوكي
شباب
ثانك يو.
انتوا لازم تعرفوا هيدي الجود اوبورتيونيتي اللي لكم تحضروا، لانه هيدي ماتيريال بيساعدكم بعدين حتى بالشغل. يعني اذا واحد بده يشتغل بالتليكوم و specifically for سيسكو. بعدين في اشي تاني كمان بدي اقول لكم اياها. اذا انتوا فتحتوا بالسايت راح تشوفوا في about professions. يعني they provide some jobs for the students, especially for the students that have high grades. يعني إذا أنتوا you prepare very well، وفي عنا كمان some competitions. في عنا طلاب يعني وصلوا لكاليفورنيا بأمريكا، يعني they get jobs. So this is also important، وبعدين راح تستفيدوا من هيدا الشيء. طيب from my side now I finish. راح تشوفوا الإيميلز about when the module 1 and 3 are active. هيدي أول exam، أنا فرجيتكم وين راح تشوفوا exam. تفتحوا and you make it. بعدين exam بياخد شي 2 hours. So في عندكم وقت منيح، بس كمان you have to prepare يعني to read the material، لأنه أوقات في كمان questions كتير قريبين يعني بالanswers. طبعا exam هو multiple choice answers موجودين، بس انتوا لازم تعرفوا أي answer أنسب واحد. Okay guys, if you don't have any questions, we finish for today. Do you have any questions? طيب, if you don't have questions, I will tell you bye, and I wish you a happy new year, and إن شاء الله يكون يعني بنخلص من كارانتين ومن بانديميا، وبنرجع لجامعة طبيعية، وبنرجع نشتغل شغل طبيعي. Okay, يلا باي باي from my side.
Goodbye, doctor.
Bye bye.